are approximately 74% of the visible universe is hydrogen. Now, if we took a light or a lamp here filled with helium, we would be able to look at the fingerprints of helium. And you know, like with fingerprints in CSI, they're all different. You can, any two people in the world, they say, has a different fingerprint. And they're distinct. And elements are the same way. Helium, you know what the brightest line in helium is? It's kind of a yellowish line. And hydrogen doesn't even have any yellow lines. But helium has a lovely one, very bright. And helium's naked eye color is kind of almost a salmonish, pinkish peach color. It's kind of cool looking. Completely different fingerprint. And third note, every element in the periodic table has a different discrete spectrum, like fingerprints. And those are the fingerprints that in CSI, that's what they look for. One of the ways that they figure out what's in, a sample, they look at the spectrum. And astronomers the same. They look at the spectrum. Yep, we've got a lot of hydrogen. Now let's go and talk about specifics. All right. So here's some more systematic notes. The four wavelengths that we just viewed are called Balmer's series, or the Balmer series for hydrogen. And the Balmer series for hydrogen has been observed for about 140 years or so. They've been studying it. The guy that figured it out, the numerical pattern, was Balmer, so they named it after him. Now, what we just saw are all in the visible band, the Roy G. Biv band. Okay, now you may say, Dr. B, who is Roy G. Biv? He is a mythical person. He doesn't exist. But we give him personhood because his name, Roy G. Biv, is the exact order of colors in the visible spectrum. Red, orange, yellow, green, right in the middle, blue, indigo, and violet. Okay? So Roy G. Biv is an easy name to remember. No one knows what his middle initial G stands for. By the way, the thermal source, the incandescent lights, emit a Roy G. Biv continuous spectrum, a rainbow. And this is a fairly good picture of it right there. Question?
I was just wondering if the Balmer series was specifically for hydrogen, or that's what you call all of the...
The Balmer series is in hydrogen, okay? But you can identify similar series in other elements, for helium and so forth. Okay, now, here's a picture. Can you go to no lights, please? Turn all the lights off. Just a minute. This one's kind of dim. It's kind of hard to see. This is an actual picture from Caltech. I applied the yellow letters there, H alpha, H beta, H gamma, H delta. Up here in the upper right, here's H alpha, the red. So this is kind of what you were able to see, or if we had a really, really dark lab with really good optics and everything and a really good diffraction rating and no greasy thumbprints on it, stuff like that, you would see something like this. Now, unfortunately, on the projectors up here, it's not very bright, but on YouTube, it's going to be very nice and bright. And go ahead with the presentation mode, thank you. H alpha. Doing a little bit of trig and stuff, we can figure out the wavelength of H alpha is 656 nanometers. Nanometers is a billionth of a meter, 10 to the minus 9 meters. A millionth of a millimeter. So as small as a millimeter is, divide that up into a million equal spots, and each one of those equal parts is a nanometer. Bria?
Did you say that was a wavelength or a wavelength?
Yeah, that's a wavelength. The wavelength of the H alpha red line, it's an electromagnetic wave, has a wavelength, and we measured out 656 nanometers. H beta, the aqua line, the other really bright one that you can see in a classroom, about 486. H gamma. Oh, now we're getting down into the purples. Those deep purpley blue ones. And those are the H gamma is 435. By the way, raise your hand if you saw those two, or at least one purpley blue line. Just to show of hands to, okay, some of you could see it, good. Right? They're very faint, so if you didn't see it, don't feel bad. They're not easy. I couldn't see them very well. But if we had really good equipment, that didn't have a lot of fingerprints on it and stuff. H delta, 410 nanometers. In fact, the Roy G. Biv band is considered to be approximately 400 nanometers to 700 nanometers. Now, you as an individual, or your cousin, or your grandpa, or any other individual in the universe, they might see wavelengths a little bit smaller than 400. So maybe, 393 nanometers. That'd be deeper into the that'd be ultraviolet for everybody, except for that person. It'd be just a deeper violet. You might be able to see a slightly larger, like 705 nanometers. And for the rest of us normal people, that would be infrared. But for you, or for your cousin or whoever it is, they might see that as a deeper red than the reddest red that you know of. Okay, so it's not like there's a fence there. It's kind of a proximate range. They say that some insects can see deeper into the infrared, longer wavelengths past 700. But for humans, it's about 400 to 700. All right, and make a note: 400 is violet, short wavelengths. 700 is red, and you can see that in 1A, H alpha, the red line it's getting up there to 700. And H delta, 1D, that was a deep purpley blue line. That's 410. Right? So it's almost down the bottom of the visible band. All right. Now, you may look at that list of wavelengths and think, Dr. B, these wavelengths, they're nice. They're very nice, very precise nanometers, but it's kind of boring. But there is a pattern. The pattern is kind of tricky. We're going to try to tackle it. And to tackle it, here's another listing. Here's the frequency set as well. 457 terahertz for H alpha. 617 terahertz, capital T hertz. 691 for H gamma, the first really purpley one. And H delta, the really, really purpley one, 732. Notice, this is something that I asked you about on the test. Notice the wavelength and frequency relationship. 656 times 457, and then 486 and 617. Lambda goes smaller, frequency goes up. 434, even smaller lambda, frequency even higher, 691. Smallest wavelength, H delta, biggest frequency. So the violet is also the highest frequency end of the visible spectrum. Red is the low frequency end. And as we'll talk about towards the end of the lecture, the lower the frequency, the lower the energy of the photon of light associated with these different wavelengths. Now, the guy that figured out the pattern, there is a pattern, the guy that figured it out about 130 years ago, something like that, is Johann Balmer from Switzerland. He was a mathematician, but he was up on physics too, and he was particularly interested in the optical behavior of hydrogen. And he figured out there is a pattern here. Now, it may not look like it. Lambda's going down, frequencies going up as you go from the top of this table to the bottom. But, you know, what is it? I mean, it's not like they double, they don't triple, it's not squaring. You know, it's kind of a gradual. But he figured out a pattern. And then Einstein and Bohr, Albert Einstein and Niels Bohr, I think we talked about Niels Bohr once already this semester. They actually gave a physics explanation for the Balmer series. Balmer figured out the formula, and then these guys figured out why that formula was there. It has to do with energy levels. Now let's take a look at a picture here. Here's the Balmer series again. This picture gives you a right triangle. And basically, if you're in a lab, Nicole, and you can measure the distance from the diffraction grating to the source, you know, so you're looking at these incandescent lights. So if you know the distance from the incandescent light down to the diffraction grating, and then if you know the spacing of all the lines in the diffraction grating, and a little bit of trig, and if you use interference concepts, specifically constructive interference, you can actually calculate the wavelength. And I could take any group of 20 of you into a lab, and if we had a bunch of lasers and some meter sticks, and if we had some staples, you know, you take a stapler and you lift it up, you take it apart, and you put new staples in when you're out. But if you take a stapler, you take out that rack of staples, very even, equal spacing. You can use that rack of staples as a diffraction grating. Another thing you can do as a diffraction grating, if you have, and I've done this in the lab, if you have a metal ruler, a small metal ruler where the millimeters or the 1/8 of an inch or 1/16 of an inch are engraved in the metal, you can use that as a diffraction grating. And with that, you can measure, do a little trig, and a little constructive interference, and bang, you can get the wavelengths. So it's not that bodacious. And those are the wavelengths. So we observe this in the lab. You know, so we're looking at the diffraction grating, we're looking at the central image, and then off to an angle to the left or to the right, we can see H alpha. So if you're in the lab, you can figure out the angle, do a little trig, figure out the wavelength. It's not too hard. Now here's the Balmer series. Here's the formula. Whoa! Look at that baby. I have no idea how Johann Balmer figured it out, but he did. He said, all right, it's not really a pattern in lambda, it's a pattern in inverse lambda, 1 over lambda. And he said, it's equal to some constant R called the Rydberg constant. We now call it the Rydberg constant. And then times a little bit of fraction arithmetic here. You know, 1 over 2 squared minus 1 over n squared. And n is allowed to have the number 3, 4, 5, or 6. Now for n equals 3, you get 1 over the wavelength of the H alpha. So you get 1 over 656. It all works. Right, and we're going to calculate this out. Right, so here's the Balmer series. All these wavelengths fit this pattern. Alpha is n equals 3, beta n equals 4, gamma n equals 5. And Balmer said, I don't know how he could have figured this out. He must have tried about a zillion different patterns before he figured this one out. I don't know. There's probably a logical way to get to it, but I wouldn't want to try it. He probably thought about it for a long time before he stumbled on it. But I bet he was really happy that he did, because now we have a formula that reveals the quantum structure of hydrogen if we analyze it correctly. Now let's do a calculation, and you're going to do some calculations with homework this weekend with Balmer's formula. So take careful notes, Lexi. Ready? Here we go. Let's verify this formula for n equals 4. Okay, here we go. There's the formula. And over here, I put, Natalie, I put n equals 4 down here. And it's 4 squared, so it's 1 over 4 squared. So that's a 16th. And then 1 over 2 squared, that's for the Balmer series, that's always 1 over 2 squared. And then the n squared, n can be 3, 4, 5, or 6. Okay? And that's the Balmer series. Right? So this is for n equals 4. And this is going to give us the wavelength of h beta. Right? Now, 1 over 2 squared is 1/4. 1 over 4 squared is 1/16. So we have a fraction problem from 6th grade. Big disaster. Okay. Oh, could you guys send your diffraction gratings to the aisles, please? Darian, could you pick them up, please? Thank you. Let's take a minute to do that. And yeah, we're going to do a little bit of fraction work here. And yup, for your homework, sorry, Camille, did you see the diffraction patterns? You came a little late. It's in web courses. We had it for homework in the YouTubes last week. All right. And Darian, when you get these, can you put rubber bands around them and stuff? I think there's a bunch of... And be very careful about those glass fragments down there. I can't believe it.
It happens.
Dr. B breaking a piece of lab equipment like a rank undergraduate. Gosh.
What do you do with the activity? You're going to show us.
Somebody's up. You guys see that m to the minus 1? Rydberg's constant. Ooh, look at that thing. 1.0974 times 10 to the 7. What? And meters to the minus 1? What? But remember, seconds to the minus 1 is a hertz. That's the unit of frequency. Okay? And this one is good. If you look on the left side of the equation, it's 1 over lambda. So my dimensions had better be 1 over meters. And that's what m to the minus 1 is. Inverse meters, 1 over meter. All right, so we're going to do that. All right, so common denominators. Let's get back to the discussion here. Common denominators, 1/4 minus 1/16. Common denominators, 16th fractions. So 1/4 is 4 over 16. 1/16 is 1 over 16. That one's already squared away. So the difference is 3/16. So what happens is that goes into the square brackets. All right, right in here. So the second line of my equation block, yep, that's 3 over 16. And now it's not looking too bad. I've got a power of 10, I've got an inverse meter, I've got a fraction, and I got 1.0974, which they can measure. It's like one of these constants of nature. It's not like a nice, 1/2 or something like that. It's just some weird number in the metric system. All right. But the thing is, we've got to invert that. That's 1 over lambda. So we've got to take those numbers and turn them upside down because we want lambda. We don't want 1 over lambda. We want lambda itself. All right. So here's 1 over lambda. All right. That's the equation we just put together. All right. Now we park this down here, and here's lambda itself. Here's the flip-flop of it. Okay. So now the top of my equation block is lambda equals, instead of 1 over lambda equals. All right, and I flip-flopped everything. And now the 16th denominator is now numerator 16. Nice. My old numerator 3 is now down the denominator. And my Rydberg constant used to be in the numerator, now it's downstairs. And now, Abigail, you were asking me, what do you do with those meters to the minus 1? Well, meters to the minus 1 in the denominator is like meters to the positive 1 in the numerator. All right? So here's what we're looking at. And 10 to the 7 in the numerator, or excuse me, 10 to the 7 in the denominator is like 10 to the minus 7 in the numerator. So that's easy. And then my numeric part here is 16 on top. And then, hey, you guys, 3 times 1.0974. Better verify that on your calculator. 3.292. I believe that's correct. Anybody verify? 3 times 1.0974. You got that? Okay, good. Anybody, you got that over there? Okay, good. Well, we got a verification. All right, so now you go 16 divided by that. All right? And really, you know, you can do all this in one move if you know what you're doing with scientific notation on your calculator, but I'm kind of spelling it out step by step if you're a little rusty in that. But yeah, 16 divided by 3.2922, that's about 4, that's almost 5, 4 point something. And it works out to 4.86 times 10 to the minus 7 meters. And my wonderful students, that is it. If I move the decimal point from 4.86 to 486, I have to go 10 to the minus 9 for my scientific notation. There it is, 486 times 10 to the minus 9, equivalent, and it's meters. And my wonderful students, that is 486 nanometers, because 10 to the minus 9 meters is a nanometer. All right. So go ahead and put a check mark. Now, your homework tonight, I'm going to ask you to do some Balmer series wavelength calculations. Remember, you use the Balmer series, get all your numbers in there, but then you got to do a flip-flop to get lambda. Not because you don't want to type in 1 over lambda. You want to get lambda itself. Question?
If you had to move the decimal to the right, how come it's not like -5?
If I,
If you're moving, well, when I look at scientific notation, I think I'm moving the decimal.
yeah. What's 10 to the minus 9 times 10 to the 2? 10 to the minus 7, right? Yeah, 10 to the minus 9 times 10 to the 2 is 10 to the minus 7. So 10 to the minus 7 is the same as 10 to the 2 times 10 to the minus 9. Right? So this is really, right here, 10 to the 2 times 10 to the minus 9. Now normally you don't think of it, and if you stopped here on a written exam, Miss Camille, you'd be perfectly fine. That would be correct. In clicking, and we're going to do some clicking in just a second, you guys, so have your clickers ready. In clicking, I have to tell you, nanometers. So you'd have to say, all right, 10 to the minus 7 is really 10 to the 2 times 10 to the minus 9. Okay, here's 10 to the minus 9. And 10 to the 2 times this is 486. All right? So yeah, it works out. All right. Another question. You're up here in the front row. DJ, you're up here in the second row. It's nice up there. You keep an eye on me up here. Okay, so here's our summary for the Balmer series. And you'll have some homework over the weekend. You'll do 1 or 2 Balmer calculations. And some Balmer concepts. And the yellow box at the lower left is really kind of our punchline, our payoff line. The observable regularity in this, it is a weird looking formula, but it is a formula. And as Galileo said, the grand book of the universe is written in mathematical language. There it is. It's not easy to sort out, but it is there. It's not too bodacious. I mean, you should see some of the the calculus equations for the theory of relativity. Oh my goodness. But even they can be simplified. The observable regularity in the Balmer series reflected in this formula means that there's some kind of an unseen regularity in the atom itself. In other words, Javier, it's not a coincidence. There is a rhyme and a reason to it. You know, so 486, 434, 656, all that stuff, the numbers, they look kind of intimidating and stuff, but actually there's a pattern. That's it. 1 over lambda equals all that stuff. That's the pattern. That's the language that nature uses to express herself for hydrogen. Now, side note, important. For another element, for other elements, it's not quite the same. This is the Balmer series for hydrogen. You can use a Balmer-like series formula or a Balmer-like formula for other elements, and capital R will be different. This is called the Rydberg constant for hydrogen. Okay, but you can make similar. We're just going to work with. You're going to work with hydrogen in the homework, and you're going to work with the previously unknown substance known as chuctanium, discovered by Chuck Norris. In other words, kind of a fictitious element. Danielle, what does the N? N is the number that's assigned to each of these lines. That's the pattern. Balmer said it's not. Like Sir Isaac Newton said, measure the mass in kilograms, measure the distance in meter, square the distance, put it in the denominator, and then you can get the force of gravity from that. But Balmer said, you don't have to measure anything. You don't have a mass. You don't have a charge. You don't have a distance. But what you do have is just a regular number. All right? And that's why this is actually the very first sign of the quantum world. Here is the spectrum of our star, the sun. If you look at it carefully, you'll see that there's all kinds of little black spots in it, or gaps. It's a rainbow with gaps. And that's the exact opposite of what you saw with hydrogen, Jihan. With hydrogen, you see a big gap with a few colors. This is a rainbow with a few, well, not a few, but quite a few colors removed. Side note, this is called an absorption spectrum. The gaps, it's kind of like you look at somebody, they have a gap in their smile, their two front teeth are a little wide apart. This one's got a lot of gaps in the smile for the sun. In the rainbow coming from the sun, if you look at it really carefully, there are gaps. There are colors that are missing. And that means that hydrogen and other elements, they're not emitting light the way that we saw up front here. They're absorbing specific colors. That's also allowed in the quantum theory of hydrogen and the quantum theory of other elements. These gaps tell you the presence of other elements, like sodium. Make a side note. We can easily see the presence of sodium in these gaps. Absorption features, we call them. Sodium absorbing. Let's see. Probably, see these two gaps right here, these two big ones? This is actually in the yellows. Sodium has two big spectral features in the yellow. There's some big ones up here in the greens. Okay, some of those might be no. Hydrogen's going to be a little bluer than that. I don't know what those greens are. But you can look at, you know what? You can't see it down here, but down towards the bottom, if you look on I'll tell you what, if you look on YouTube, you'll see down here towards the bottom, right above the letter P in spectrum, right in here, you'll see a big gap, and I believe that's the H alpha absorption feature. Every gap in here corresponds to an absorption line from an element that we know of in the periodic table, except for a few gaps that 100 years ago, or maybe a little more than 100 years ago, we didn't know what those gaps were. We didn't know it wasn't sodium, it wasn't hydrogen, it wasn't carbon, it wasn't oxygen. We can see all those elements up here. You know, it wasn't titanium. It wasn't, all these, the first few levels of the periodic table. We didn't know what it was. But you know what it ended up being? It ended up being helium, a new element. They discovered it in the absorption features. They could account for every other gap in the spectrum except for a few, and they said, this has got to be an element, and we're going to call it helium because we discovered it on the sun. Helios, the sun. And by God, they found it later when they looked at natural gas coming up from oil wells and stuff like that, and mines. Helium is a natural gas from the beginning of the universe until today. Matter of fact, approximately 24% of the visible universe is helium. 75%, 74, 75% right in there, hydrogen. 24%, something like that, helium. And the last 1%, everything else. So about 1 point something percent of the visible universe, carbon, oxygen, nitrogen, sodium, magnesium, lithium, iron. All the iron, everybody that's sitting in a chair it's made of steel. Steel's mostly iron, a little bit of carbon. Silicon, it's all in your computers, your laptop, your phones, all that silicon in the electronics. It's that last 1% of the visible universe. It's kind of amazing. Now here on Earth, the proportions are not quite like that. But in the universe at large, yeah, we can see that. So let's talk about the quantum structure of hydrogen. Go ahead and draw a picture of a hydrogen. And I've got 4 energy levels mapped out. Good. Kind of a simplified view. And it looks like planets orbiting a star. And we now know that the atom is not quite that simple, but it's a good starting point. And here's the beginning of the quantum theory of hydrogen, that only certain orbital levels are allowed, that electrons only live at certain specific altitudes and no others, and that each altitude, of course, has a specific set electrical potential energy. And we even made a list of those. The n equals 1 level for hydrogen has the lowest potential energy, and in electron volts, it's negative 13.6. And then n equals 2 had a little bit bigger, still negative, but not quite as deep in the negatives. N equals 3, n equals 4. And we listed that, and we listed out n equals infinity, 0. And we talked about the binding energy of the ground state, negative 13.6 electron volts. The ionization energy of the hydrogen atom, 13.6 will ionize every hydrogen atom in the universe. So if you zap it with 13.6 electron volts of energy, you're going to strip that electron out, no matter if it's in the ground state or any other state. The energy levels in a quantum system are countable. Right? N equals 1, n equals 2, n equals 3. In other words, it's discrete. It's not continuous. You can't have just any old altitude. You can only have these, well, not just these 4, but a countable set. And after that, you're ionized. You're free. You don't have a hydrogen anymore. Okay? Now, the other thing is that the orbits, well, if you have an electron that changes its orbit, it makes a quantum leap. It will jump, for instance, from n equals 3 down to n equals 2. It will emit a photon. And we now know that the transition from n equals 3 down to n equals 2 is the transition between orbital levels that emits a red H alpha photon. Now, if you go from n equals 3 down to n equals 1, that's going to be, I believe, an ultraviolet. But n equals 3, the Balmer series is everything that ends at n equals 2. And that's why somebody was asking me, Bria, I think, it's 1 over 2 squared. That's the end point. All the transitions go from n equals 3 down to n equals 2, n equals 4 down to n equals 2, n equals 5 down to n equals 2, and on up. They all come down and end up on n equals 2 for the Balmer series. Okay, so when they jump downwards, they emit. So there goes that red photon outwards. All right? So when the electron transitions downward. Now, if exactly that color of photon hits the electron, it'll blaze it from n equals 2 back up to n equals 3. That's absorption. Let me repeat that. The absorption process that produces gaps in the spectrum of the sun, for instance, is when the exact color for the transition, n equals 2 to n equals 3, for instance, comes to the atom and zaps it from n equals 2 back up to n equals 3. Then the photon is absorbed. If it's the right color, if it delivers the right amount of energy. Other colors, no. But certain colors, yes. They have the right energy, bam. They'll boost it up from n equals 3 to n equals 2. So incoming, absorbed, boosts the energy level upward. Dropping to a lower orbit, losing energy, photon goes outward. The guys that figured this all out, you can read about it in chapter 9, are Niels Bohr and Albert Einstein. Well, not the only guys, but they're the biggest contributors to it, the quantum theory of hydrogen. And here's the thing that they decided to use. Planck's constant. Einstein said, let's think of the atom as emitting photons of light for which the energy is Planck's constant times a frequency. What? Yeah, Planck's constant, baby. They figured, you see, Planck was thinking about thermal radiation. Planck was thinking about the spectrum of these incandescent light sources. He wasn't thinking about hydrogen at the time. Later, of course, he did, and everybody did. Everybody's thinking about hydrogen. Niels Bohr and Einstein. Here they are at some conference, talking about the weather or who knows what, smoking their pipes. Now, the reason that Planck's constant was used is the following. This is something that we didn't mention in chapter 8, but I'll mention it now. And that is the source of the electromagnetic field. Electromagnetic waves are generated by accelerating electric charges. Oscillating electric charges, whether an electron or a proton, will generate waves. Right? And the person that figured that out in the 1800s was Maxwell. The person that first produced it in the lab was a guy named Hertz, Heinrich Hertz, in Germany. And that is why the unit of frequency is named after him. He designed an electrical system that oscillated, and he said it's going to produce electromagnetic radiation at a certain frequency, and he was able to measure it. Nowadays, we take it for granted, but the guy that first did it in the lab and showed that it could be done was Hertz. Now, the guy that began applying it to matter is Max Planck. He was studying About 1899. Thermal radiation, incandescent light source. Nobody could figure out the intensity distribution of the rainbow. You have something like the sun, a certain temperature emits certain colors. Certain colors are brighter, certain colors are not as bright. The most energy from the sun, you know what color it comes through? Actually, let me ask you a question. Dear, you want to do this question? Clicker question. Number 1 for today. Of all the Roy G. Biv colors, so you can type in a word, red, orange, yellow, green, blue, indigo, or violet, or a letter, ROYGBIV. Of all the colors, which color carries the most joules per second, the most energy from the sun to the earth? Is it red? So in other words, are the most joules per second blazing through the red part of the spectrum? Or the O, the Y, the G, the BI, or the V? Okay, now I'm going to give go ahead and type in an answer. I see some people typing in words. You can type in a letter. And I'm going to mark everybody correct. Just give me, because this is kind of like a survey. So just give me your best guess. Your best educated guess. From the surface of the sun, red carries the most energy per second. Or orange carries the most. Or whatever. What color is it? Well, who is typing in the letter P? P is not part of purple. No, red. Oh, Roy G. Vip. No, Roy G. Bip. It's not Roy G. Bip. It's Roy G. Biv. Violet. Don't use the word purple. I bet there's some wise guy putting in Bob here or something. All right, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, switch over to the display. Please, thank you. All right, now here's somebody with purple. R, that's red. Ooh, a lot of reds. Ooh, look at that, red. 18, no, stop there. 18% is 39%. That's 57%. That's the majority. V, ultraviolet. Ultraviolet, no good. I'm not going to count that correct, but that's not in the visible band. V, viol, okay. Violet. Y, yeah, okay, yellow. Red. Let's see what else we got. I, green.
Those are all.
You know what? I'm not going to ask for a show of hands, but only one person got the right answer. Green. Green is the light. Now, the other colors, they do a good job, but the most energy per second comes to the green band of visible light. And nobody could figure that out except Max Planck. So he made a specific assumption about quantized electron oscillations in a hot thermal object that was incandescent. And basically it was this. He said, let the energy not be proportional to the maximum extension of the oscillation. So don't look at how far left and right the electron is going, or the atom is going, or the ion, or whatever charge is oscillating. Just look at the frequency. He said the energy is going to be this, it's got to be proportional to frequency. If it is, I can explain the entire distribution of energy from the sun. You know, green being the prime channel and all the other colors. And he said, if E is equal to HF, some constant times F, then it all works. And from that, he was able to figure out the value for his constant, Planck's constant. Energy in joules, here's the value of H, 6.63 times 10 to the minus 34. And next week, in our homework and in class, we'll do a calculation with Planck's constant. All right? And we're going to need to use it a couple times. Frequency of the oscillators in hertz. All right? 6.63 times 10 to the minus 34 joule seconds. It's actually a little bit easier to work with in electron volt seconds, so we'll use that on the homework. We'll work on that next week, not this weekend. And Einstein said, let hydrogen atoms use the same formula. That's why he said that. Einstein said, look, if E is equal to HF for oscillating charges in an incandescent object, why don't we try that for hydrogen? The electrons, they're not, they're orbiting. It's not a thermal object. It's, pure hydrogen. It emits a spectrum. If we zap it with voltage, but it's not necessarily hot. So let's try to do that. And it worked out for him. Now, the guy that figured it out for electrons was de Broglie. But let's take a look at Planck's constant. As I like to call it and describe it, one constant to rule them all. Here's the size of Planck's constant, the quantum of action. And we will use that in electron volt seconds when it gets to homework next week. So here's the conundrum. All right, Einstein. Nice. Energy levels, Niels Bohr, different altitudes, good. But why does nature choose those? Okay, I believe you. The energy levels work, but why? Why are only those allowed? What physical process selects those altitudes from every other? Einstein and Planck said, yeah, these altitudes, these energy levels have to exist. The photons come out at the right wavelength, but we don't know why only those are allowed. The guy that figured that out was Louis de Broglie, and the supposition that he made was simply this. Why not treat the electron bound to the proton in the nucleus as a wave? And then he said this. If the electron is a wave, let it occupy only those orbits for which the energy, the momentum, and the wavelength fits to produce constructive interference. And remember, when Darian and I were doing the coil spring demonstration, we didn't get standing waves until we hit just the right frequency. And that's what de Broglie figured out. He said, look, if you do just the right frequency, just the right wavelength, you'll get constructive interference, and it will obey the Coulomb interaction. Constructive interference. If the electron behaves as a wave and constructively interferes with itself, you've got a reason for nature choosing specific orbits. Because just like with Darian, certain frequencies only. Same thing with a guitar string. And here's a note. We know it's true for guitars. There's nothing special about that. So here's the formula. This is called the de Broglie relation. The wavelength, go ahead and jot this down in your notes. The wavelength of the electron is Planck's constant divided by mv, the momentum. And remember what momentum? That comes out of Newton's second law? Yup. Same momentum. But now it's in a quantum context using Planck's constant to give you a wavelength. So the size of the momentum the Coulomb interaction itself, control the exact orbits that an electron may occupy, and only those orbits. Now, last question before we dismiss is simply this. All right, Dr. B, I thought the electron was a particle. If it's really a wave, shouldn't it diffract? Will an electron diffract? If I send an electron through a diffraction grating, will it diffract? We'll talk about that on Monday. The answer is yes. Okay, homework 17 over the weekend. You're dismissed. I'll see you next week. Lights, please. Thank you. Microphone, please. Microphone off. Yeah.
An exam on Tuesday.
I want everybody to stop.
I need to come to class on Tuesday. I need to practice.
If you were sick, you missed it. I mean, it was online. We didn't even have it in class. Yeah. I made announcements in web courses.
Thursday.
Hold on a second.